Okay, welcome to today's video about series circuits. We spent the last class talking about electric current just in general and looking at some relationships between current, voltage, and resistance. Today we're going to look at the simplest type of circuit. That would be a series circuit. To construct a series circuit, all you have to have is a battery connected by wires to one or more resistors or lamps for our purposes under one condition. Okay? The reason this is the simplest type of circuit is because there must be only one path for current to flow through. There can only be one path for that current to flow through. Okay? So, some examples of series circuits. I'm going to draw 3 different series circuits just to kind of show you some different types. We know that every circuit has to have a power source, so a battery or a cell, depending on what you want to draw, has to be connected by wires to some sort of power or energy consumer. And remember, so wires are just lines that you draw. This is the symbol for a resistor. This is the simplest series circuit you can have, a battery with one resistor. You could also have something like this. Here's a battery with 2 resistors. Okay? And it's a series circuit because there is no alternate path for the current to flow through. Current leaves this end of the battery, flows through resistor 1, flows through resistor 2, and then back into the battery. There's no second path that the current can flow through. There's no alternate path for the moving charges. I'm sure you know where I'm going with this. We can have 3 resistors in a series circuit. We can really have as many as you want. Okay? You can have as many resistors in a series circuit as you possibly want. Now, in any circuit, okay, there are 3 measurable things. 3 things that we measure a lot of, or at least we're going to talk about for right now. You can measure voltage differences, which I'm just going to shorten to voltage. You can remember the voltage. You can measure the voltage difference between 2 points. You can measure the current flowing past a certain point, and you can measure the resistance of some object in the circuit. Now, for series circuits, there are some rules that must be followed. Okay? There are a few rules regarding how the voltage and the current and the resistance interact. First one, total voltage drop or gain. The sum of all of the voltage drops across all resistors or lamps is equal to the voltage gain of the battery. Now, this is actually specified by an equation in your reference tables, and I'll show you that right now. Let me just flip to the reference table section for electricity. Okay, if you've noticed, we've actually covered almost everything. We've actually almost covered everything in electricity. The only things we haven't covered, we've gotten all the equations up to here. We know the circuit symbols. We know the resistivities, what they mean. The only things we haven't covered are this equation, and the 2 sections on series and parallel circuits. Well, today, we're going to look at series and parallel circuits. And the equation I want to draw your attention to right now is this one. V equals V1 plus V2 plus V3 plus ... That might just seem like kind of a random thing to write, but this is what it's referring to, the total voltage drop or gain. So what I like to write is Vt for V total equals voltage V1 plus V2 plus V3 plus ... That is your reminder in the reference tables of how the voltage drops for different parts of a series circuit work when we have a series circuit, and how they compare to the voltage gain or the total voltage of the circuit or the voltage gain of the battery. What we find is that if you were to take the voltage drop for all 3, or for however many resistors you have, and add it up, that's the total voltage drop of the circuit, and that should be equal to the voltage gain for the battery. So, let me show you how this works. We have a circuit over here, and in this circuit, you can see that right now, let me focus it a little better for you. In this circuit right now, we have a 10 ohm resistor, 2 10 ohm resistors, and a 9 volt battery. Okay? This is a voltmeter. Remember, it measures voltage for us. What I want to do is I want to connect the voltmeter. I want to put the probes around some piece of the circuit that causes a voltage drop. So for instance, this resistor. And I should get a reading on the voltmeter, 4.5 volts. Good. Notice that I always put the red one before the thing that uses voltage and the black one after. Watch what happens if I switch their places. Nothing really major, you just get a negative sign up there. So red should always go leading into the thing that has the voltage drop, black goes after it. Now I can do the same thing over here on this resistor, and that voltage drop is also 4.5. As a matter of fact, if I look at the voltage drop across both, so I put the red lead before the first resistor and the black lead after the second resistor, I get the sum, 4.5 plus 4.5 equals 9 volts. And if you look at the battery, this is a 9 volt battery, meaning that current that flows through the battery has a voltage gain of 9 volts. Now, this doesn't just work when we have kind of random, when we have really nice equal resistors. We can also do this with different voltages and different resistors. So let's crank up the voltage, I don't know, let's make it 20. Let's make this, I don't know, 25. And let's make this one, I don't know, how about 7? Okay. So you can see some changes to the circuit. You can actually see if you look very closely, the red arrows seem like they're moving a little faster. That's kind of implying that there's a greater current right now. So let's look at the voltage drops again. Voltage drop across the 25 ohm resistor is 15.62. The voltage drop across the 7 ohm resistor is 4.37. Now, if I add those together, 15, oh, there we go, 0.62 plus 4.37, I get 19.99. There's probably some rounding going on right there. If I were to look at the voltage drop across the whole thing, okay, 19.99 should round to about 20 volts. And again, we have a 20 volt battery. This will even be the same if I were to add in another resistor. Let's add in a 10 ohm resistor. Okay, so now look what I have. My voltage drops have changed, 11.9. 3.33, and 4.76. Crap, I forgot what the first one was. You see that the total is 20. Okay, 11.9, 3.33, 4.76. Again, very, very close to 20, and you see that 20 is the voltage gain that the battery has. The voltage, the total, not the voltage drop for a battery. Batteries don't cause voltage drops, they cause voltage gains. So again, we see that the total voltage gain for the circuit is equal to the sum of the voltage drops across all resistors. That's a total voltage, and that's equal to the voltage gain of the battery. Okay, rule number 1. Now, rule number 2. The individual voltage drop across a resistor is equal to this equation right here. V equals IR. And this is known as Ohm's law. Now, you might not recognize this equation right away, but if we look at the reference tables, we see that it's just a rearrangement of this, the definition of resistance. This is called Ohm's law. It's very, very important. It's probably the most important equation in circuits. What it says is that the voltage drop for some part of a circuit is equal to the current that moves through the resistor, okay, the number of charges per second that flow past it, multiplied by its resistance, okay? So it's just a little bit of a rearrangement of what we were doing earlier. Once you know the resistance of something, you can predict what the voltage drop is if you also know the current. So let me just write that out for you. voltage drop equals current through resistor times resistance. Okay. All right, and we can actually see this whenever we look at any of these individual resistors. Okay. Now, so what we're going to do, let's go back to our simulation, and it's time to bring the current in here. Okay. We can predict the voltage drop if we know the current and the resistance. So, the resistance of this first resistor is 25 ohms. And if we use this little cheating current tool here, we look at the current going in. Oh, notice that the current going in, it doesn't matter where we put it, the current going in and out seems to be the same, 0.48. And the one thing I don't like about this simulation is it rounds that current too much. Okay, we should have a slightly better prediction of what the current is, but that's okay. So if we take the resistance and multiply by the current, so 25 times 0.48, we get 12. Now, if we look at the voltage across that resistor, 11.9, yeah, pretty close to 12. We can do the same thing with the 7 ohm resistor. Let's check out the current there. Seems to be about 0.48 again. So we do 7 times 0.48, get about 3.36. Remember what we got? 3.33, very similar. Again, there's just some rounding with the current there that's throwing us off a little bit. And finally, last but not least, we're going to measure the current, the voltage drop for the 10 ohm resistor. But you can do this one in your head. 10 times 0.48, 4.8. And we see that this voltage is 4.76, which does round to 4.8. So we see that Ohm's law works in predicting the voltage for any of these resistors. Okay, the voltage drop is equal to the current through the resistor multiplied by the resistance. All right. By the way, notice something about the current. That is probably the defining feature of a series circuit, is its current. And the reason it's so important is that the current in a series circuit is the same everywhere. We just saw that. Now, don't confuse this, okay? This does not mean that the current can never change. Because watch what happens if I increase the voltage, okay? If I increase the voltage, if I bring it up, look at that current. That current is definitely changing, okay? What we are talking about right here is that for a particular series circuit that has a set voltage and a set, we call it equivalent resistance, and we'll talk about that in a second, the current is the same at all locations. Matter of fact, even if we actually measure the current the way we're supposed to, not just with this kind of magic sensor, let's get this out of the way, but if we measure the current the way we're supposed to, by inserting what's known as an ammeter directly into the circuit at multiple places, we get 0.48. Let's put it somewhere else. Let's put it after this resistor. We get 0.48. Let's put it before this resistor. Not that. We get 0.48. So the current anywhere in a series circuit is going to be the same. Oh, there's one thing I didn't notice. The current's also going to be sensitive to what the resistance of the circuit is, the overall resistance. Because see, if I change any one of the resistors, that's going to change the amount of current that flows through. Okay? All right. We'll actually stop there. We'll do another video in just a little bit where we go over the last two rules and we finally start doing some examples.